Flick a rope once, and something races down it, yet not a single piece of rope actually travels with that thing. If you've ever watched a slow-motion clip of a wave on a string, it almost looks like a little creature running along the rope, like the rope made a bump and then sent the bump on a trip. And your eyes don't help you here, because they're trained to track objects. We're incredibly good at watching a ball fly across a room. So when a shape moves, your brain quietly treats the shape like an object. But now do a simple test. Put a tiny piece of tape on the rope at one spot, just a little marker. Flick the rope again and keep your eyes on the tape. The bump goes by. The tape does not travel with it. The tape goes up, maybe sideways a hair, then back down, and it ends almost exactly where it started. So what exactly moved? That's the part your textbook usually didn't slow down to answer. It gave you names, wavelength, frequency, amplitude. It drew a sine curve and said, here is a wave. And if you did well in the class, you learned to calculate things about that curve. But the uncomfortable truth is, a wave is not a thing. The way a rock is a thing. It's not a bump object. A wave is a process. It's a pattern of change spreading through a system, because each part of that system follows a simple local rule. And that's why waves show up everywhere. Not because nature has a preference for wiggly lines, but because nature is built out of parts that only talk to nearby parts, and those parts have inertia. When you combine local influence with can't respond instantly, disturbances don't teleport, they propagate. In the next half hour, I want to do something very specific. I want you to be able to say out loud, without vague poetry, what a wave really is. Not just what it looks like, but what mechanism makes it inevitable. And I want you to see that the same core idea is what links a rope, a sound, a radio signal, and yes, the quantum wave that people talk about with that slightly suspicious tone. And I'll be careful. If we don't know a why in some deeper sense, I'll say so. If we can simplify something without lying, we will. If we can't, we won't. Most of us were taught to label waves, wavelength, frequency, amplitude, without ever being told what, physically, is doing the traveling. Here's what most people currently believe, even if they don't say it out loud. They believe a wave is a moving oscillation. They picture something in the medium going forward, like the water itself is marching toward the shore, or the air itself is flowing across the room from a speaker, or the rope itself is sliding along as the wave passes. And that belief feels reasonable because we watch the crest of a water wave move, and it looks like a little hill of water traveling. But if you watch a leaf floating on the surface while a wave passes, the leaf mostly bobs up and down. It doesn't get carried to the beach by one wave. It might drift slowly due to other effects, but the wave itself is not a conveyor belt of water. So already we have a tension. The thing you see moving isn't necessarily the same as the stuff you imagine moving. Now here's the trick that clears the fog. You must separate two ideas that your brain wants to merge, the motion of the material and the motion of the pattern. Let's separate two motions you've been accidentally mixing, the motion of the material and the motion of the pattern. Think about a line of people waiting at a coffee shop. Everyone is standing still, more or less. Now one person steps forward because the line advances. Then the next person steps forward. Then the next. Something moved down the line. You can point to it. The gap moved. The empty space that used to be between person A and the counter shifts backward as people fill it. That gap travels from the front of the line toward the back. But what is the gap made of? It's made of sorts or nothing. It's not a substance. Yet it has a position, it has a speed, and you can even time it. You can say, that gap traveled from the front to me in 5 seconds. That's a pattern moving through a system of people who each follow a local rule. When the person in front of you moves, you move. Or take a stadium wave. Thousands of people stand up and sit down. The wave sweeps around the arena. It looks like a single thing sliding along the crowd. But nobody runs around the stadium. Each person does a little up and down motion. The traveling wave is the coordination pattern, not a migrating pile of humans. Once you accept that a moving pattern can be real, in the sense of having a speed and carrying something important, you're ready for waves. On a rope, the material points are the tape markers. Their job is to move locally up and down or side to side depending on the type of wave. The wave is the organization of those local motions into a traveling pattern. Now I can hear a reasonable objection. You might say, fine, it's a pattern, but a pattern of what? What's the thing that's being passed along? Good. That's exactly the right question. Because the deep essence of a wave is not wiggle. The deep essence is transfer. Transfer of energy and transfer of information about a disturbance from one region to the next. When you flick the rope, you inject energy into it. The rope doesn't keep that energy stuck at your hand. It doesn't move the whole rope forward either. Instead, because of how the rope is connected, that energy spreads along. It spreads in a very organized way that looks like a traveling pulse. So what's being passed along is not rope. It's a state of motion and tension. It's a local change that forces the next part to respond. If you want the simplest description of a traveling wave, you can say this. There is some quantity that depends on position and time. Call it yxt, if you like, that represents the displacement of the rope at each point. A traveling wave is when that displacement pattern keeps its shape as it moves, like a shape sliding along the x-axis. That's why you see expressions like a function of x-ct. That's not fancy. It just means because the pattern at position x now is the same as the pattern that was at position x-ct earlier. It is a mathematical way of saying shape moving at speed c. But notice something. That statement by itself doesn't tell you why the rope should behave that way. It's a description, not a mechanism. So now we go after the mechanism. Here's the secret mechanism. Each little piece only feels its neighbors, and that single rule forces a disturbance to spread. Imagine not a continuous rope, but a row of office chairs connected by bungee cords. Chair 1 is connected to Chair 2 with a stretchy cord. Chair 2 is connected to Chair 3, and so on down a hallway. Now you give Chair 1 a shove to the right and let go. What happens? Chair 1 moves right. The bungee to Chair 2 stretches. That stretching pulls on Chair 2. But Chair 2 doesn't respond instantly with infinite speed because Chair 2 has inertia. It has mass. So it starts to move. It starts late. It starts after Chair 1 has already moved some. Then Chair 2's motion stretches the bungee to Chair 3. That pulls on Chair 3. Chair 3 responds late. You have just built a wave machine. No sine curves required. No wave vocabulary required. It's just cause and effect passed locally down the chain. And notice what this guarantees. The disturbance cannot skip chairs. Chair 20 cannot feel Chair 1 directly. Chair 20 only feels Chair 19, so whatever influence travels down the hallway has to be handed off from neighbor to neighbor. This is why I said waves are bookkeeping for local causality. If nature only allows local interactions, then disturbances spread by neighbor handoffs, and what you see is a wave. Now let's upgrade the chairs into something more rope-like. Instead of chairs that move only sideways, imagine small beads threaded on a string, each bead connected to its neighbors by little springs. Or just keep thinking of the rope itself as made of many tiny connected segments. Each segment has mass, that's inertia. Each segment is connected to the next, that's coupling. When one segment is displaced, the connection exerts a restoring force. That restoring force depends on how different the segment is from its neighbor, and this is the crucial part. The restoring force depends on differences. If two neighboring segments are displaced the same amount, there's no stretch between them, no extra force due to the coupling. So the coupling responds to spatial variations. That one phrase, the coupling responds to spatial variations, is the seed of the wave equation. If you go to a physics class that derives the wave equation, what you'll see is Newton's second law on a small segment. Mass times acceleration equals net force. The net force comes from tension and curvature for a string, or pressure differences for sound, or electric and magnetic field relationships for electromagnetic waves. The details differ, but the structure is always the same. Acceleration in time is driven by curvature or gradient in space, and that's what makes waves. If you want a simple mental form, it's like saying, if the line is curved, it wants to straighten, and the straightening creates motion. But the motion overshoots because of inertia, and that overshoot creates curvature somewhere else, and so on. It's a continual conversion between stored energy in the coupling, like stretched springs or tension, and kinetic energy of motion. On a rope, when you flick it, you create a region where the rope is bent. That means tension forces are not balanced. The rope segment feels a sideways pull that tries to reduce the bend. It accelerates, but it doesn't stop exactly at the straight position because it has momentum. It overshoots. That overshoot creates bend on the other side. And now the imbalance is in a nearby region. So the action continues down the rope. That's the propagation. Now here's a sneaky point that textbooks sometimes let you glide past. When you say a wave travels, you might imagine some substance moving forward, but in this mechanism, what moves forward is the region where the coupling energy and motion energy are exchanging. It's like a traveling zone of action. Energy is not a substance either, but it is transferred in a measurable way. You can measure the power flow down a string. You can measure the intensity of a sound wave. You can measure the energy carried by an electromagnetic wave as it hits a solar panel. So the wave is real in the sense that it carries energy and momentum, even if no chunk of matter makes the trip. At this point, you might ask, why do we end up with such neat traveling shapes? Why aren't waves just messy, spreading jitters? Great. That question takes us to one of the most important, never-revealed ideas: normal modes. If you want to know what a system likes to do, you look for the motions that don't get scrambled as they evolve. Imagine you're trying to predict the future of that hallway of bungee-connected chairs. You shove one chair and soon everything is moving, pulling, oscillating, seeming complicated. But there's a trick nature gives you. In many systems, especially linear ones, there are special patterns of motion that are stable in character. They don't get tangled up into other patterns. If the system starts in one of these patterns, it stays in that kind of pattern, just with changing phase. Those special patterns are called normal modes. On a guitar string, the normal modes are the standing wave shapes, the fundamental, the second harmonic, the third, and so on. Each one is a clean note. If you manage to excite only one mode, the string vibrates in that shape. In our chain of coupled oscillators, there are also normal modes. They look like waves with definite wavelengths along the chain, where each mass oscillates with the same frequency, but with a phase shift from neighbor to neighbor. Now here's the part that people often miss. Sine waves are not what a wave is. Sine waves are what a linear system turns into when you look for patterns that stay themselves. They're the system's eigenfunctions, the pure notes, the basis, and the reason they matter is superposition. If the equations are linear, which is often a very good approximation for small disturbances, then if pattern A is a possible motion and pattern B is a possible motion, then A plus B is also a possible motion. That's not a philosophical statement. It's a property of the equations. It's why two ripples can pass through each other and continue on rather than colliding like billiard balls and shattering into nonsense. So what happens when you flick the rope and create some arbitrary pulse shape? That shape is not a pure mode. It's a mixture. It can be decomposed into a sum of many sine-like components of different wavelengths. Each component travels according to the rules of the system, and the observed pulse is what you get when you add all those components back together at each time. This is the music view of waves. Your initial disturbance is a chord. The system evolves each note. The chord changes in time. And this view is not optional if you want to understand interference, diffraction, beats, and dispersion. It's the backbone. Let's make it concrete with beats, because beats are one of the easiest places to feel superposition in your bones. If you play two tones that are close in frequency, you hear a wah-wah-wah pulsing of loudness. That's not the sound wave speeding up and slowing down. It's the addition of two waves that sometimes line up and sometimes partially cancel. At some moments, crest meets crest and the amplitude adds. At other moments, crest meets trough and they subtract. The result is a wave whose fast oscillation is modulated by a slower envelope. That envelope is the beat. The key point is the medium is still just doing what it always does, oscillating locally. The fancy behavior is in the pattern created by adding waves. Now, modes. If you hold a string at both ends, you constrain it. Not every traveling wave fits. Only certain wavelengths fit neatly between the fixed ends. So the system selects discrete normal modes. That's why instruments produce discrete notes. This is again the system telling you these are the patterns that behave cleanly. And now we're ready for a twist. Up to now it sounds like waves are almost too nice. Disturbance propagates in components, superposition, clean modes, but real waves often don't behave so politely. Pulses spread out, signals smear, colors separate. That's dispersion. Now, for the part textbooks often hide in a footnote, in many real materials, different wavelengths don't travel together. Take a ripple on deep water. You've probably seen this. A disturbance creates a packet of waves, and as it travels, it seems to stretch with different ripples moving at different speeds. The packet changes shape. Or think of light going through a prism. White light enters and colors emerge at different angles. That's because different wavelengths travel differently through the glass. If every sine component traveled at the same speed, then an arbitrary pulse would keep its shape perfectly. It would be a traveling rigid pattern. But if different wavelengths travel at different speeds, then the components get out of sync over time. When you add them back together, the pulse spreads. This is why the "a wave travels at speed v" statement can be a half-truth. It's true for a single sine wave component in many contexts. A pure frequency component has a phase velocity. You can track a crest and assign it a speed. But a real signal, like a hand flick or a spoken syllable, is not one pure sine wave. It's a packet. It has a range of frequencies, and the speed at which the packet, the envelope, the energy transfer travels is usually the group velocity. Now, we have to be careful and not make this mystical. Phase velocity is about the movement of the peaks of a sinusoidal component. Group velocity is about the movement of the overall modulation that results from adding components. In many ordinary situations, the group velocity is the meaningful signal speed, but the full truth depends on the medium and how the signal is shaped. If you start talking about information speed in exotic cases, you need precise definitions, so we'll keep it grounded. Pulses can spread because components travel differently, and here's why dispersion belongs in this video. It's the proof that the sine curve is not the definition of a wave. If it were, you'd be stuck. But because waves are fundamentally about the evolution of disturbances in coupled systems, dispersion is just one more property of that evolution. It's not weird. It's the system's rulebook expressed through different frequencies. Okay, so far we've treated waves as disturbances in a medium: ropes, air, water. Now we ask the big question that makes people uneasy. So what exactly is waving when there's no rope, like in light moving through empty space? If waves are disturbances that propagate by neighbor-to-neighbor influence, what could be the neighbors in empty space? For a long time, people tried to answer that by inventing a medium for light, the ether, a substance filling space that could carry electromagnetic waves. But that idea ran into trouble because it implied you could move relative to the ether and detect your motion by measuring how light speed changes. Experiments didn't support that in the expected way. Modern physics do. It doesn't need an ether medium for light. Instead, the thing that exists at every point in space is a field, the electromagnetic field. A field is not a substance you scoop into a bucket. It's a physical quantity with a value at each point in space and time. The electric field has a direction and magnitude, the magnetic field too. And Maxwell's equations are the local rule. They tell you how changes in the electric field relate to changes in the magnetic field and vice versa, locally in space. And once again, you get the same structure. Time changes are driven by spatial variations. Local coupling plus inertia-like behavior in the field dynamics gives wave propagation. So light is a wave because a disturbance in the electromagnetic field propagates, not because little bits of ether are wobbling. The field itself is the thing that has a state at each point, and that state can change and hand off change to nearby points. Now you might say, fine, but is the field real? Here's a practical answer that is very Feynman-like. If something carries energy and momentum, and it can push on charges, and you can measure its effects, then whatever philosophical label you put on it, you have to treat it as physically significant. Light carries energy and momentum. It exerts radiation pressure, it can heat things, it can transfer information. The field description makes precise predictions, so in physics, we take it seriously. Now comes the most dangerous bridge: quantum waves. When people hear wave in quantum mechanics, they often import all the medium intuition and then get confused. They imagine an electron is literally smeared like a fog in space, sloshing around, sometimes collapsing mysteriously. There is something right and something wrong in that picture. Here is the honest core. Quantum mechanics uses a wave-like mathematical object, often called the wave function, that evolves according to a wave equation, the Schrödinger equation for many cases. That object is a probability amplitude. Its magnitude squared gives probabilities for outcomes. So it behaves like a wave in the sense of superposition and interference. Two possibilities can add like waves. That's why you get interference patterns with electrons and photons. It is not just a metaphor, but it is not a wave in a material medium. And it's not even a wave of energy density in the same straightforward way as an EM wave, because the wave function is not directly an observable field you measure at a point with a probe. What you measure are outcomes. The wave function is a tool that predicts the statistics of outcomes. And Feynman's attitude here is refreshingly blunt. We can compute what happens. We can predict interference. But the picture you choose, particle-like or wave-like, is a model with limits. Sometimes one is more useful. Neither is the full story in the everyday sense. So in quantum physics, what is waving is a new kind of thing, an amplitude, a rule for probabilities, evolving locally through an equation that enforces a kind of causality in how the state changes across space. If you keep that straight, you avoid the worst confusion. You stop asking what at medium is the electron wave made of, and start asking, what does this wave-like evolution predict, and how do superposition and interference show up in outcomes? Now, we've built all the pieces: pattern, not thing, local coupling, modes and superposition, dispersion and packets, field waves, quantum amplitudes. So what is the one-sentence reveal? A wave is what you inevitably get when a system has inertia and local restoring rules. A disturbance can only move by handing its change to the next place. Let's tie it together slowly, because this is the moment the title promised. A wave is not a wiggly object. It's not a sine curve traveling. Those are images. A wave is the time evolution of a disturbance in a system where, 1, there is something that can store energy locally and exchange it with motion. In a string, tension stores energy when stretched. In sound, compression stores energy in pressure. In electromagnetism, electric and magnetic fields store energy. In quantum mechanics, the state stores a kind of amplitude structure that evolves. 2, interactions are local. Each region influences nearby regions according to a rule. 3, inertia exists. Stuff does not respond instantly. It accelerates, overshoots, oscillates. When those are true, disturbances propagate, and if the system is linear or close to linear, those disturbances can be decomposed into modes that behave cleanly. That's why sine waves are powerful. They are the pure notes the system knows how to play. And superposition is what makes waves feel different from objects. Two waves can occupy the same place and pass through because what's adding is not material substance but displacement, pressure variation, field value, amplitude, things that can add. Now remember the tape on the rope. The tape doesn't travel, yet the wave travels. What traveled was the pattern of displacement, and with it a flow of energy. That energy hopped from segment to segment through coupling. That's what waves really are. And it immediately gives you a new way to look at the world. A traffic jam is a wave. Cars can move forward while the jam pattern moves backward. A rumor in a crowd is a wave. Electrical signals in a circuit are waves. The brightness flicker in two overlapping sound sources is a beat wave. The pattern on a pond is a wave. The radio signal is a wave in the electromagnetic field. And the interference pattern in a double-slit experiment is evidence of wave-like superposition in probability amplitudes. Once you start seeing waves as rules propagating through a system, you'll notice them everywhere: traffic, crowds, circuits, even the colors in a soap bubble. And here's a final thought to leave you with, because it captures the spirit of this whole subject. When you ask, what is a wave, you're really asking, how does change move through the world? Objects are one way to carry change. A rock moves from here to there, but waves are another way. A pattern of change moves, carried by many local elements, each doing only a small motion. And physics, at its best, is learning when the universe uses objects, when it uses waves, and when it uses something that refuses to be neatly either one, yet still follows precise rules we can test. If you want a fun experiment after this video, take any situation where something moves and ask, is matter moving or is a pattern moving? Then ask, what local rule is handing the change from neighbor to neighbor? That question alone will make you see the world differently.